Hello, multivariable calculus students. This is Mr. Johnson, and this is section 10.5, which is on parametric surfaces. So we're going to start with looking at just the generic idea here of a parametric surface. And remember, we've worked with space curves where we have a vector valued function that has one variable, like t, for example, or theta, or something like that, and we can graph a space curve using that vector function, and it just traces out values. So for example, if you had an axis that looked like this, and let's say that you have your vector valued function r of t, whatever that may be, what's happening is that you would maybe put in 1 for t, and you would get a point in space, and then you would have another vector, let's say that it's r of 2, so you put in 2 for t, and you have another point in space, and you just continue this process. Maybe this is r of 3, for example, and you put a point in space, and these points then are connected in the form of a space curve like that. Okay, the way we're going to change this now is that we're going to have two parameters for our vector valued function. And so not only are we going to be able to get these space curves along a surface, but we're able to go in either direction because of the multiple variables. So for example, if we're looking at our equation here and our generic values are u and v, if u is held as a constant, and so the only variable that changes is v, you would get simply a space curve on a surface. If u varies and v is held as a constant, then you would get a space curve in the other kind of direction. And together, all of those, as they change, will build a surface in space. So there's a little visual down here that maybe will help make a little bit more sense. So if we have a particular surface, let's say that we want to let one of the two variables be a constant, we may get these curves that might look like this along the surface based on one variable changing and the other one being constant values. So for example, if you let u be 1 and v varied, if you let u be 2 and v varied, if you let u be 3 and v varied, you might get these curves like that along the surface. If you did the other way around, so if you were to, for example, let u vary and v is 1, you might get a curve that looks like this. And if u varies and v is 2, you might get a curve that looks like that, or so on and so forth. And so you're making these different contour curves along the surface, and together they form an entire surface. And that's what we're looking at now. So again, we're changing from having one variable of a vector function to two variables of vector function. Every single component of the vector valued function, so x and y and z, are obviously made up of u and v. Now, you may have a situation, I'll show you examples of this, where x is maybe made up of one equation of just u and there is not a v represented, or vice versa with the other ones. That's okay. So if x, for example, is equal to, I don't know, like sine of u, and y is equal to v, and z is equal to cosine of u, that just means that with the component of x, we don't have v being impacting on it. V could be anything with this particular component. Now with y, v is based on y, but u is not a part of that equation, which means u can be anything with regard to that component, and so on. So there's a lot of variety here as we look at these different components of the vector valued function. So let's go ahead and take a look at a couple examples. Now what I'm going to do, and what is already in Schoology, is some visuals of the first couple graphs. So you can go to those videos. I wasn't able to embed them in the exact same video you're watching right now, but those visuals are really short, just a couple minutes. And what it is a nice graph of this particular surface. And I show you examples of where you can let certain values be constants and you get different curves along this particular surface. Let me give you just a quick example of what I'm talking about. So let's say, well, first of all, our component x of uv is equal to 2 cosine u, and then y of uv is equal to v, and z of uv is equal to 2 sine of u. So if you maybe were to let's pick an easy one. Let's let let v equal 0. So if v equals 0, if we're looking just at x and z, and we were to take x squared plus z squared, that would give us 2 cosine u squared plus 2 sine u squared, which gives us 4 cosine squared u plus 4 sine squared u, and we can see this trig identity would equal 4. In other words, if v was 0, we would have a circle that had a radius of 4, and you can see kind of really lightly in this diagram, you can see this little trace of that exact contour on this surface. It looks like this. And you can identify the different points that it will go through. So if v was 0, and remember y is equal to v, that's our second component in the equation. So if y was 0, then we get a circle that is kind of on this plane y equals 0. So envision a plane slicing this cylinder at y equals 0. You would have this intersection. We've talked about these space curve intersections of surfaces. So you would have a plane at y equals 0 intersecting the cylinder, that surface, and what we would get in return is this space curve that I have in red. And that is just one of many, 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 many curves that make up this surface. So I'm going to show you in that video, so just you can even pause this and go to that video and take a look. But if you were to do the other way around, if you were to let, for example, u be a constant and v was to vary, you'll actually get these lines along this particular cylinder. So that would occur if u is a number. So let's say u is 1 and v varies, you will get these lines. And if you were to let, v be 1 or 2 or something like that, you would get other curves, other circles. Like for instance, you might have one like right here, for example, if y was 2 or something like that. Again, if you were to do this infinitely and have all these different circles with all these different lines and they were all to combine, you would get this cylinder in space. So again, that video outlines that. It's a nice app, nice visual. I also talk about the second part where what if we were to restrict our u and v values? So what if we were to let u be from 0 to pi over 2 and v was from 0 to 3? Well, that's going to restrict the values of x, y, and z that we would get in our parametric equation. And we would end up getting a little section of this particular cylinder. So, again, if we were to go back up to the large picture here, we would be kind of focusing on this little section right here based on the restriction of the domain. So there are different benefits of this as we look at these graphs, especially with graphs that are maybe a little bit more unique, ones that are harder to graph in our traditional system. The vector valued function is actually a nice tool to be able to graph them smoothly. Okay, let's move on to the next page. All right, much of what I talked about on the previous page is written up here at the top. And that is specifically if you were to look at u varying with v being a constant versus v varying with u being a constant, you get different curves that form along the surface. And here's just an example of two visuals here. So if you were to look at these two particular curves, if you were to mimic this process over and over again, you would get additional curves along the surface. And you'll see that in the visual that I have in that other video, that app, is that you see all these contours form and it creates all together as you put them together this nice, clean, neat surface. Here's another kind of unique one, and again, I'll just refer you to the video that I posted here. It's just a minute or two long, and it just shows you this kind of cool looking. It almost looks like a noodle, I think, where you have this helix-like graph, but it's a combination of these helix curves along with these circles. And you can see in your diagram that if u was held constant, then you get all of these circles as a part of the surface. If v is held constant, you end up getting these helix curves along the surface, and as you put them together, it forms the entire three-dimensional object. So take a look at that video. It's really short. All right, let's move on to example 2. So in example 2, what we have is a connection between the equation for a plane that we've been talking about in Cartesian form. Remember that equation is a times x minus x sub naught plus b times y minus y sub naught plus c times z minus z sub naught. And this is the Cartesian equation that we've used so much so far, especially in chapter 9. And what I'm going to do is show you an equation for a plane in vector form. So we're going to have another option here, and this will be a vector, a two-variable vector equation that represents this particular surface. So the way we're going to start this is that we're going to look at a plane that consists of vectors A and B. So those red vectors that you see in the diagram are A and B. And we also have a point, we're going to call it P sub naught, and we'll have an additional point out here. This point out here is just a generic XYZ point. It could be any point along the plane. And this initial one is going to be x sub 0, y sub 0, and z sub 0. It's sort of what we would consider the initial point. Now, there are two values that are multiplying a and b. So a is only this little vector right here, and b is just this vector right here. But what we want is the ability to scale a and scale b in order to come up with an equation for this long vector between p sub naught and p. So if you can envision multiplying a by a value, some number, you would extend a out to here, and then with b, you would travel along b, but you would have to scale that as well to get to p. So in other words, the equation that I'm defining here is going to be for the vector p sub naught to p, that vector would be equal to a scaled vector of A plus a scaled vector of B. And so if we put those together, we get that vector P sub naught to P. Okay. Now let's go ahead and draw in. I want to try to create the visual of our coordinate system. I'm actually going to erase this point just for a moment. Let's say that our z-axis is here, and our x-axis and our y-axis. And let's say that we have a vector r sub naught that leads us to this initial point. So the initial r sub naught vector, we've used this one many, many times. Basically, it's a way for us to get to the plane in space. So from the position vector, okay? So envision what's happening here. We're going to travel out to this particular point using r sub naught, and then we're going to travel along A and along B in order to identify some point that is on the plane. Now, if we were to change U and change V, so if we were to scale them differently, maybe we travel along this vector r sub naught, and we travel along here, and maybe we end right there and put a point. Or maybe we actually scale it even further and end there and put a point. Or we scale it and end over here and put a point. Or over here and put a point. And you can see that based on the variance of A and B, we're able to travel along to the plane, and then we're able to basically use any scale of these vectors in order to put as many points as we want along this particular plane, forming the entire plane in space. So we're traveling along one vector, we're using two other vectors to end at some point on the plane. And if we do that infinitely, we get every point along the plane. We end up creating the surface. So algebraically, here's what's happening. We're setting up a vector equation using u and v as our variables, and we have our initial vector r sub naught. I'll write this two different ways. So we have our initial vector r sub naught, and we are going to add the vector p sub naught and p. So we're adding this particular vector that we just formed in order to land on any given point that we want. Because remember, p sub naught doesn't vary, but p does. The point p varies. I'm just going to rewrite that as r sub naught plus, instead of p sub naught and p, I'm going to use u times a and v times b. And I'm going to put this into component form. So r sub naught is x sub naught, y sub naught, z sub naught. U is a scalar, obviously. For vector A, I'm just going to make it a sub 1 and a sub 2 and a sub 3. And then we have v times, I'm going to make this b sub 1 and b sub 2 and then b sub 3. And I'll just put this together in complete component form. So our vector equation for a plane would be the initial x plus u times a sub 1 plus v times b sub 1 y sub naught plus u times a sub 2 plus v b sub 2, and then z sub naught plus u a sub 3 plus v b sub 3. And this is now a representation of a plane. So we have now a vector representation of a plane, as well as what we've been building for the last chapter and a half, which is our Cartesian equation for a plane. So it's an additional equation for a particular surface that we've had. Okay, let's move on to the next page. All right, so we just talked about how we've had for a long time our Cartesian equation for a plane, and now we have a substitute vector equation for a plane. We're going to do this with a sphere. So with a sphere, we have the generic equation in rectangular form for a sphere, which is going to be x squared plus y squared plus z squared is equal to the radius of the sphere squared. I'm going to show you a vector representation for this. And this actually is from, I'll make a note here, this is from section 9.7, where we talked about spherical coordinates. And if you remember, the x value or the x conversion to spherical coordinates was the radius, which in this case is a, times sine of phi times cosine theta. And then y was the radius times sine of phi times sine of theta. And z is a times cosine of phi. And that, again, that's just from section 9.7. So if we were to come up with a vector equation for a sphere with two variables, we could write it as the vector r of phi and theta. Those are our two variables we're using. And we have the x component a sine of phi, cosine theta, a sine of phi, sine of theta, and a cosine phi. And that would graph our equation for a sphere. Keep in mind, you could change the variables if you wanted to be the standard u and v variables. So you would have a sine of u cosine of v, a sine of u sine of v, and a cosine of u. You could change it to other variables as well. It doesn't matter at all. Keep in mind that a is the radius, which won't vary. Okay, that will be a numeric value. So it's really just a vector function of two variables. Now, one of the questions is, why does it matter? Why is it helpful to have a vector function? Well, graphing surfaces that are complex is actually much more manageable with vectors than it is with our Cartesian setup. And so if you were to graph a sphere in many computer generated programs in the form of x squared plus y squared plus z squared is equal to a squared, you often need to have many apps, for example, or programs, you need to actually solve for z, which gives you this two-set equation. So you have a squared minus x squared minus y squared. And often when we do that, we end up actually getting a graph that looks a little bit funky. It looks like this, where there are these goofy these goofy sections not showing up. And one of the main reasons for that is that there are vertical sections of the graph, and many programs have a difficult time graphing those. Your calculator, for example, is a perfect example of that. Obviously, your calculator cannot graph a three-dimensional object, but if you ever try to graph a circle on a calculator where you solve for the top of the circle and the bottom of the circle and graph it as two different functions, those graphs never touch because your calculator cannot draw that vertical line. So there are issues with surfaces that are complex when it comes to our Cartesian approach because of the vertical aspects of those surfaces. But if you have, for instance, any kind of design, I know I had a T-shirt made for the National Honor Society, and I gave them the artwork to put on the T-shirt, and they needed a vector valued document. They needed the artwork to be in vector form rather than more of a standard kind of Word document form, because in order to graph nice smooth curves and nice smooth surfaces, the vector valued equations are much neater than a Cartesian style equation. And so, obviously we don't want to look at a sphere that has all these gaps in it. We want to look at a nice clean sphere, and that's often what a vector function can provide for us. All right, let's move on to example 4. So we're going to look at, again, I'm pulling out examples that we've done in the past. We've done cylinders using rectangular form. That's right here. So obviously, if we were to graph this particular cylinder, z would vary indefinitely. So z would be anything we want it to be, and x and y are going to be dependent on this equation, x squared plus y squared is equal to 4. And we've talked about this many times where we could set up for x 2 cosine theta, for example, and y could be 2 sine theta, and that would be the trig identity that would satisfy our equation. Now the challenge is that z is something entirely different. Z is not based on the angle. Z is kind of its own variable. So one of our options could be to simply use theta and then you use z for itself. So for example, x could be 2 cosine theta and y could be 2 sine theta, and z could simply just be its own variable defined. Or let's say we wanted to go with the standard u and v, then we could have 2 cosine of u and 2 sine of u and v. That would be fine as well. You could use all sorts of other things in terms of variables, but the idea is that you're letting x and y vary based on our restriction, and then z can be essentially any variable. Okay, let's move on and look at two more. All right, example 5, we're looking at elliptical paraboloid, and again, we've talked about this type of surface, and so we're looking at trying to create a vector valued function that would graph that particular surface. Now, if you notice, all x, y, and z's are all together in the same equation. So one technique we could use is actually to let x and y be their own parameters. So for example, we could have the vector valued function x and y, where x is itself, y is itself, and then z is simply just the equation that we have for z. That would work. It seems almost too easy to be true, but that does define this particular elliptical paraboloid fully. You could change into the standard u and v form, and you could get simply u, v, and u squared plus 2v squared. That would work as well. Now keep in mind that with, if you're thinking of any kind of trig identity here, you're in a little bit of trouble because of the 2. So you want to be careful to not force something into x and y that would end up adjusting our value. And that's why we want to try to keep it a little bit simple. Okay, let's try example 6. We're going to look at the surface z equals 2 times the square root of x squared plus y squared. So it's the top half of a cone. And we could go with the route of letting x and y be their own parameters again. And one of the reasons is that, z and x and y are all part of the same equation here. So we could write a vector valued function that would look like this, where x is itself, y is itself, and z is simply the equation that we have written. That would work. Another option, because we do have the situation where x squared plus y squared is written in, as we've seen the trig identities before, so we could let x equal, now we don't know the radius, so we've got to be careful. It's going to be r, let's say r cosine theta, y could be r sine theta. Now if that's the case, z would be 2 times the square root of r squared cosine squared plus r squared sine squared, and that would simplify to 2 times the square root of, because cosine squared plus sine squared is 1, we would get the square root of r squared, which means z would be simply 2r. Obviously this approach is more complex, but this could be another option where you have the variables r and theta, and again you could change those to any, you could make it u and v or whatever you want, but x is r cosine theta, r sine theta, and z is 2r. And obviously it looks very different than the other one, but that would also represent this surface using a vector valued function. Okay, this section as a whole is really just a kind of intro to what we're going to study in the next couple chapters. And so this just kind of scratches the surface, but I hope that's helpful, and that's it for section 10.5. Thank you.